Let's look at MCA Chief Mates Stability and Structures, July 2019, question number 2. It says a box-shaped vessel floating at an even keel in salt water has the following particulars: length 100 meters, breadth 21 meters, draft 5.9 meters, kg 8.95 meters. An empty amidship double bottom watertight compartment 18 meters long, height of 6.6 meters, and extending full breadth of vessel is bilged. Calculate each of the following: A. The final draft. B. The change in GM. We'll first of all make the drawing for this question. So this is the box-shaped vessel whose length is 100 meters. This is the breadth of the vessel, which is 21 meters. This is the initial water line. So this becomes the initial draft, which is 5.9 meters. This is the length of the compartment, which is 18 meters. This is the height of the compartment, which is from the keel to the watertight flat. So this is watertight flat. And this is the keel. So the height is 6.6 meters. When we solve the bilging question by lost buoyancy constant displacement method, we make the following assumptions. So we'll write assuming kg constant, underwater volume constant, displacement constant. Now when we do this thing, which is common to all the bilging questions, we now have to make another assumption, which is in respect to where the final waterline lies. So the final waterline may lie below the watertight flat, or the final waterline may lie above the watertight flat, which we don't know which is the case. So we have to make one of the assumptions and solve accordingly. If that assumption at the end doesn't hold good, then we have to cancel out everything and solve with the other remaining method. So in this case, we are assuming final water line is below the watertight flat. So this is the watertight flat, and we are assuming that the final water line is below the watertight flat. So buoyancy lost is equals to buoyancy gain. So buoyancy lost is basically this part, which is the small l, which is the length of the compartment, multiplied by capital B, which is the breadth of the vessel since it extends the full breadth of the vessel, times the draft, which is 5.9 meters, which is this value, is equals to buoyancy gain. Now this lost buoyancy will be gained somewhere on the vessel. Now if the final water line lies below the watertight flat, which we had made the assumption, so this part would be the gained buoyancy part from here till here. So to take this thing into consideration, we will first get the intact or the bilge length. So the bilge length, I would say it is capital L minus small l. So this was the capital L, which is the length of the vessel, intact length, and this is the length of the compartment. So whatever we'll get after bilging would be just this part and this part, which is excluding this part. So this is given by 100 minus 18 times the breadth of the vessel, which is 21 meters, times the sink gauge. When we solve it further, we'll get 18 multiplied by 21 multiplied by 5.9 equals to 82, which is by solving this bracket multiplied by 21 multiplied by the sink gauge. Now we will take this 82 multiplied by 21, which is on the right hand side of the equation, to the left hand side of the equation. If this value was being multiplied, which is the case, it will go in division when it is moved to the left hand side of the equation. So this is how this value is going to move. So we'll get finally as 18 multiplied by 21 multiplied by 5.9, divided by 82 multiplied by 21 equals to sinkage. From this, we got the sinkage as 1.295 meters. Now we know our initial draft and we know our sinkage, so we can calculate the final draft. So final draft is equals to initial draft plus sinkage. So final draft is equals to 5.9 meters, which was given in the question, and sinkage is 1.295 meters, which has come from this place, which has given us the final draft as 7.195 meters. Now the next thing what we need to do is to plot this draft on our diagram. So let's move back to our diagram. We know that from keel to this watertight flat is 6.6 meters, and to plot the bilge draft, which is over 6.6 meters, it has to be the final water line, and this has to be the bilge draft, which is quite clear in this case that the bilge draft is more than the height of the watertight flat. But our assumption was that the final or bilge water line is below the watertight flat, which is somewhere here. But this is not the case when we solved this part of the question, which means that our assumption was incorrect. All this part was incorrect. So we'll write down the statement. Our assumption on final water line below watertight flat was incorrect. Therefore, buoyancy lost is equals to buoyancy gain, which is again this is the same part. So buoyancy lost is small l multiplied by capital B multiplied by the draft, which is this part in the diagram. And if we look at buoyancy gain, it says length times breadth times sinkage minus small l times capital B times the ullage. Now, in order to understand how this comes up, we need to go back to our drawing. Going back to our drawing, if this was the case, let's assume this was our final water line. And if this is the final water line, then the buoyancy which has been gained is from here to this part, which exclude this bit. So all we need to do is, first of all, to calculate the volume of this part and subtract volume of this part, which will give us the buoyancy gain. That's what we are doing in the question. So this length times breadth times sinkage is basically the volume of the bigger cuboid, which we had seen in the diagram just before this. And this small l times capital B times the ullage is the volume of the smaller cuboid, which we had seen before this diagram. So capital L is 100 meters, breadth is 21 meters, sinkage is what we are supposed to find out. Small l is 18 meters, capital B is 21 meters, and ullage is 6.6 minus 5.9 meters. Now, I would like to emphasize on this bit of the question. Let's look at the drawing again to understand this bit. We are now assuming the final water line to be above the watertight flat because our initial assumption was wrong. So we need to subtract this small cuboid out from this bigger cuboid. If we need to subtract this small cuboid, I know the length, I know the breadth, which is 21, and height is this part, which is 6.6 minus 5.9, which will give me this part. That's what we have done. So it is 6.6 minus 5.9. So 6.6 minus 5.9 gives us 0.7. Now we'll take this equation on the left hand side. When it goes on the left hand side of the equation, since this was subtraction here, it will go and add on the left hand side of the equation. So this bit is carry forwarded again, which is 18 multiplied by 21 multiplied by 5.9. Now plus this entire part which has come back here, which is 18 times 21 times 0.7. Now what is left on the right hand side is just this bit, which is 100 times 21 times sinkage. When we solve this bit, we get 2230.2, and when we solve this part, we get 264.6. And on the right hand side of the equation, we solve this numerical bit, which is 100 times 21, where we get 2100, and sinkage stays as it is. When we calculate for the sinkage, we'll add up these two numbers, which has given us 2494.8, and we'll take this 2100, which is on the right hand side of the equation, to the left hand side of the equation, and this time it will go with division because it has been with multiplication when it was on the right hand side of the equation. So it is 2494.8 divided by 2100 equals to sinkage. So 1.188 meters is equals to the sinkage. So final draft is equals to initial draft plus sinkage. So final draft is equals to 5.9 meters, which was the initial draft of the vessel, which was given in the question, plus sinkage, which is 1.188 meters, which has come from this part. This has given us the final draft as 7.088 meters. So this is the answer for part A of the question. We'll now calculate part B of the question, which asks us to calculate the change in GM. To start with this question, we'll first calculate KB intact. So KB intact is equals to draft intact divided by 2, which is 5.9 divided by 2, which gives us 2.95 meters. The next step is to calculate BM intact. So BM intact is calculated by LB cube divided by 12V. So the intact length was 100 meters, the breadth is 21 meters, so it is 100 multiplied by 21 cube divided by 12 times the volume. So volume is length multiplied by breadth multiplied by the draft. So this is the length of the vessel, which is 100 meters, times breadth, which is 21 meters, times the draft, which is 5.9 meters. When we solve this part, we get BM intact as 6.229 meters. Now KM intact is equals to KB intact plus BM intact. So KB intact is 2.950 meters, which has come from this part, and BM intact is equals to 6.229 meters, which has come from this part. So we can say that KM intact is equals to 9.179 meters, which we have got by adding these two numbers. Now we'll solve for calculating KB in the bilged condition. Now it is of utmost importance to know that when we can use the formula draft divided by 2 and when we need to make these kind of tables. As a thumb hand rule, to understand this thing, we need to go back to our drawing. So as a thumb hand rule, if your initial water line was below the watertight flat and your final water line is also below the watertight flat, you can simply use the formula. And if your initial water line is below the watertight flat and final water line is above the watertight flat, at that time you need to use your tables. If you use the formula, that is principally incorrect and you would be penalized accordingly during the examination. Since we know that the final water line was above the watertight flat, so we'll be using the tables to calculate KB. So let's go back to our tables. So we have made the following columns, which is description, volume in meter cube, kb in meters, and moments, which is meter to the power of 4, because we get it by multiplying meter cube times meter, which is meter to the power of 4. We'll now look at the bilged vessel. So bilged vessel's length is 100 meters times 21, which is the breadth of the vessel, and this is the bilged draft, which is 7.088 meters. Now if we assume this vessel to be floating freely in the water, then its kb would be exactly at the geometric center, which is 3.544 meters, which is half of its draft. We will get its associated moments by multiplying this number times this number, which will give us this. We'll now subtract the lost volume, which is the length of the compartment multiplied by the breadth of the compartment multiplied by the height of the compartment. So the length of the compartment was 18 meters and breadth was 21 meters and height was 6.6 meters. And the geometric center, the kb of that particular compartment, if we look at the drawing again, so this is the compartment which had been flooded. So kb of that particular compartment would again be at the geometric center measured from the keel. So the kb of the compartment would be 6.6 divided by 2. So we'll look back into the tables. We have written kb as 3.3 and the associated moments is 8232.8, which we have got by multiplying these two numbers. Now the total is, the volume is 100, which is the length of the vessel, times breadth, which is 21, times the initial draft. This will always be equal to this value. Alternatively, if you don't remember this, you can straight away get a numerical value by solving this number and write it down separately, and you can get a numerical value by solving out this number and write it down separately, and simply take off this number from the above. You'll get exactly the same answer. I have written this equation here because in the very beginning we had assumed the volume to be constant. So my final volume has to be equals to the initial volume because it is assumed to be constant. The final moment is 44518.9, which is obtained by taking out this number from this number. And we will now calculate kb bilged for this table. So kb bilged will be sum of all the moments divided by sum of all the volume. So sum of all the moments is 44518.9, which has been obtained from here, and sum of all the volume, which is 12390, which has been obtained by solving this value. This has given us the kb of 3.593 meters. Now bm bilged is equals to the bilge length times the breadth cube divided by 12v. Now since the final water line was above the watertight flat and the bilge length remained intact, it is 100 meters times 21 cube divided by 12v. So this is 12 times length, which is 100 meters, times breadth, which is 21 meters, times draft, which is 5.9 meters. Which has given us a value of 6.229 meters. To understand why we have taken the length as 100 meters, we need to look at our drawing again. So let's look at the drawing. As per our initial calculations, we found out that the final water line is above the watertight flat. In this particular case, the length of the vessel at this water line is the complete length, which is 100 meters. That is why we are writing the length for calculating BM as 100 meters. If it would have been the case of final water line below the watertight flat, then in this case the length of the vessel in the bilge condition would have been written as this entire length minus this length. But this is not the case. The case is where the final water line is above the watertight flat, where the bilge length is still the same, which is 100 meters. So km bilged is equals to kb bilged plus bm bilged. So kb bilged is 3.593 meters, which has been obtained from here. And bm bilged is equals to 6.229 meters, which has been obtained from here. So km bilged is equals to 9.822 meters, which is sum of these two numbers. Now change in gm is equals to change in km, because for calculating the bilging quotient by the lost buoyancy constant displacement method, we had initially made an assumption of kg constant, displacement constant, and underwater volume constant. So if kg hasn't changed, the whatever has been changed is the gm, so that we can calculate it as the change in gm. So change in gm is equals to km bilged minus km intact. So change in gm is equals to km bilged, which is 9.822 meters, which has been obtained from here, and km intact, which is 9.179 meters, which has been obtained from here. So change in gm is equals to 0.643 meters, which has increased because when we take 9.179 out of 9.822, we'll get 0.643 meters. And it has increased because the km bilged is more than the km intact, which is the answer to the question of part B. Now, there is another catch in this question. If we look at the drawing above, and we have understood that this is the initial water line and this is the final water line. So it is quite clear in both these cases that in initial water line, the length of the vessel was same, which was 100 meters, and breadth was also same, which is 21 meters. And in the final water line, the length was also same, which is 100 meters, and breadth was 21 meters. If we know this case, then we know that BM of a vessel is dependent upon the length and breadth, which hasn't been changed both in the initial and the bilge condition. If they haven't changed, that means we'll get the same value for BM intact equals to BM bilged. If BM intact and BM bilged hasn't changed and they are equal to each other, then any change in KB would be equals to change in GM. So if we look at the question again, the part B of the solution, then we would see that BM intact was 6.229 meters and BM bilged was also 6.229 meters, and it hasn't changed because of the fact which has been said just before. So we can write it as any change in KB is equals to change in GM. And if we solve by this method, that is also acceptable, provided we give an explanation that there is no change in BM because of no change in water plane area. So the final answer is change in GM is equals to 0.643 meters, which has increased. And that's the answer for part B of this question.